Hello everyone. We back again with a new video of the course Deep Learning with the TensorFlow and Keras. In the previous video we wrote a code for a simple neural network model. We're just using the softmax. And we use it for the digit classification on MNIST database. So, and at the end we got an accuracy of 92% with the loss on the testing data, and the loss function of the 0.2026 as you can see here. And then it's the value, the accuracy for the each epoch. And also that's the loss function that you can see there. So here we saw it just it printed the accuracy and the loss for the training and the testing, but we wanted to see these values on a graph. So, and it will be easier for us to do our analysis on that. So for that, we can use TensorBoard. This is one of the function of the TensorFlow that we can use. We can use it for this. So to use TensorBoard, actually we can say we don't touch or a script to making our model, but we just import the TensorBoard library here, as you can see, the TensorBoard, and then we should define a name for our model. Here you can see we just wrote softmax model, and then we can call it, or we can use it for this the TensorBoard. When we use the TensorBoard, we should save the log of our model. So we define a directory, the path of the log, and the format that's or the name of our model that will go there. So if you see, I have a folder logs old. So I run these codes once on my computer, and I saved logs on there and define it as a logs old. And for the new one, the name is just logs. So I did it because some of the codes that we will see, it take time to run, for example, in 100 epochs. So I just saved the logs on that, and we show what happens if you run more than, for example, 100 or 200 epochs on our model. So, but back to this code, we add these 3 lines to make a name for our model and save the logs. And then when we wanted to fit our model, we just say callback TensorBoard. You can see here, callback TensorBoard, and it automatically make a folder named logs, and then it saves the logs of the model with the name that you define on that folder. So if I run the codes here, you can see if you go to the cell tab, you can run all of them instead of one by one, and it will goes when it goes 1, 2, 3. It for the first time it will take a little time because it make a folder for this and a folder to save the logs on that, and then go, and then when we call it, so the same as before, it goes for the 10 epochs. But when you want to see your graph, you can write again in terminal TensorBoard logs dir equal to lux. Okay. What happened? Let's see. Okay. Lux tensor board. Lux dir lux. Okay. It should. Okay. Sorry. But okay, and then it generate a URL link. You can save, copy it, and for example, paste it in a new tab. And here you can see for your model accuracy and also the loss. These two are for our training model, and then for the validation accuracy here, and for the validation loss that you can see here. Even if you enter a star, you can see all of them in one frame. But I recommend you to run this on Google Chrome. It's easier to use it there instead of Internet Explorer. So here you can see it's much better. So you can see validation loss and validation accuracy and how it behave. Okay, so for example, for the validation accuracy, you can see it starts from around 90% at the beginning, and then it goes to the around 92.8, something like this. But here, the real results is like this. With some fluctuations, but we can with the TensorBoard we can do the smoothing, for example, with the smoothing of 0.6, and it's just a smooth or graph. So, and also for the lows, we can see how it's reduced over the epochs. So here we have as an x-axis we have epochs, and here as we have the loss function. So it's like this. And if I want to back to our codes. So, and we saw that okay, this is how we did it. So it was, I defined epoch of 100, and this is still working, but I can stop it at this point. We don't need to go more for that. And then in the terminal, for that we can call lux alt. Okay, it's call it, and then again we can see the link and back to this. So okay, it just shows all of them. So we don't need this one, we don't need this one, we don't need this one as well. We will talk about the rest later. So and also we don't need this one. Okay, here you see it. We have the accuracy, or 100 epochs, and for the validation loss also we have it here. Okay, let's. Oh, okay, what happened? Okay, it doesn't matter. So we can see validation loss and validation. Okay, it's open it. Validation loss here, that it start from almost 0.3. It goes down, decrease, and then again after I can say that 20 epochs it goes up. That we call it overfitting. We will discuss about this in the next slides. And then it's for the accuracy. That's almost saturated at the around 92.8. This is the value. And when we put the cursor here, you can see here that it say that okay, for this model it's smooth, and the accuracy, the first parameter, it's 92 point I can say 7. So it's 0.927. So it's 92.7. So it's this, and you can do any analysis on this one. So now we saw that how we can implement a simple model, just softmax using the softmax layer for classification. Now we want to go more deep for our model. So if I back to the PowerPoint, to our slides. So we wanted to go more deep. So what does it mean? What we wanted to do here? So we use the same image or the same database. Again, we stretch it from 28 by 28 pixel to 784 and feed it to the network. But instead of using just one softmax layer, we add more layers in the middle. So one layer and several layers that you can add. They call it we can call it hidden layer. So for our example, we use 5 fully connected layers. We call these fully connected layers, or we can also say hidden layers. So we have the input. We have 5 hidden layers, and at the end we have a softmax model, similar to the previous one with the 10 class. For the activation, as you saw for the previous example, we use the activation of softmax. Let's give a probability to each class of this. But for the hidden layers or for the fully connected layers, we don't need to assign the probability for that. So like softmax, but we can use other functions to make it activation. That is used that we can use the sigmoid for that, and for the last layer we can use softmax layer. So let's back to our Jupyter notebook and see how we can do with such a deep model. So let me to close our simple model or softmax model, and then fully connected softmax layer. So similar to the previous one, we call the database and we divided it to the train and test. It's almost the same. Here for the next block, it's again almost the same. Let me run one by one. For the second block, it's almost the same. Here, as we wanted to save it on the to use it on the tensor board, we can call it, for example, fully connected softmax. And then for the next one, reshaping the image, similar to the previous one, normalization. Okay, convert it to one hot encoding output. And here, the only difference with our last example is in the sequential or defining our model. So here we use a dense, that is it should be equal for the number of neurons that we have. For example, we consider 200. In the last example we used 10, equal to number of our class, but here we use 200. So, and the input shape of this layer is equal to 784, equal to the number of pixels on our image. And then for the activation, we use the sigmoid. For the next layer, we can define 100. It can be any numbers. You should also consider the capacity of your computer. If you don't have a GPU, you cannot increase it to, for example, 500, 600, or so on. So be careful about this. And the input shape of this layer is equal to the output layer of the previous layer. That is 200. It's based on the size of the previous layer. And again, for the next layer, for example, 60. And the input shape is equal to 100 from the previous one, and 30, and plus, and the input will be 60. And for the last, and for all of them, we use the sigmoid. Here, you can see for all these four layers, we used sigmoid as an activation. But for the last layer, that's equal to the number of our class, the softmax, similar to the previous example. Softmax 10 neurons, and the activation, that is the softmax for do the classification. So usually for these fully connected layers, we use a model like this. It goes from a high number of neurons in the first layer, and then it's reduced to the number of our classes. For example, here you see that it was 200, and for the next layer we use 100, and again 60, 30, and then 10. So it goes like this usually. So when we make this model, the next blocks, so let me to run it. Next blocks, again the same as the previous one. So let me to reduce number of epoch to 5. That's fine. And then we call back the tensor board. So if I run it, and on the same number of data, and you see it takes more time. So I have a GPU on my laptop, but if you don't have a GPU, it takes more times on this. So here you see that at the second epoch, you can reach here. You can reach the accuracy of 93% almost. 93.8 or 0.938, and 95, 96. Okay, it's at the end of the or epochs, or the fifth epoch, we have accuracy of around 96%. You see, it's improved around almost, I can say, 5%. So, and if you consider that you are using this model on post offices, as it's basically used it in the post offices of the US at 1998. If you assume that, okay, with the 92%, the simple one, it means a lot of letters will back to the center, as it couldn't detect the zip code of the destination. So you see it's not good at all. So, but by this we reach to the accuracy of 96.5 almost. And then if we wanted to see the results on a graph, so we can see here that, okay, see, even for the training, we have more accuracy. If we wanted to compare these two together, here for the fully connected softmax and for the softmax model, we saw that, okay, even the training accuracy is much improved. It goes to 0.9999, and for the softmax it was 0.93. And then for the loss function, let me to adjust this. For the loss function, even for the training, we see that okay, this is this more reduced, and for the validation or for the test accuracy, you can see for the fully connected plus softmax, we have this improvement between these two here. You can see we have this improvement here. And if we have a look at the loss function, you can see okay, it's almost saturated here at the 0.3 for the loss function, but for the loss function of the fully connected layer plus softmax, it goes to almost 0.1. That is the much good improvement for this. Okay, so we almost finished this video at this point. That we are happy we had an improvement. But for the next videos, I will show you how you can even improve it much more and more, and how we can reduce the loss function more and more. So thank you for watching. See you on next video.